So welcome again, everyone. Last time we talked about statistical multiplexing, and we talked about how many users can be supported in a given multi-access situation or in a given network without regard to any buffering. Basically, we focused on the probability of overflow or probability of service denial. Now, if we allow buffering in networks, we will be able to talk about queuing delay, and that will allow us to come up with sort of average case values for the network, how loaded the network is, and how the average delay looks like. So in order to do that, we will use queuing models. And in order to study queuing models, we'll have to remember a little about Markov chains. I believe all of you here have some prior knowledge about Markov chains. If not, I can give you some resources to read. The textbook already has a pretty comprehensive discussion. But if you need to, I can lead you to other sources. But so basically, we'll go through everything essentially that we need for the purposes of this course really concisely. Okay, so X sub k is a discrete stochastic process taking values in a countable set. Let me make this a little bit finer. A countable set S, which we call a state space. Suppose X sub k basically is a process. Now, X sub k is a discrete time Markov chain when the probability that X sub k takes the value ik, given that X sub k minus 1 was at ik minus 1 and xk minus 2 is at ik minus 2 and so on, is equal to what? Maybe you can help me here. So given the previous value attained by this process and the one more previous value before that, like even especially basically given the whole history of the process, the distribution of the next value attained by this process is given by the distribution given conditioned basically on the immediate past. Basically, the definition of a Markov chain is the distribution depends on the past only through the most immediate past, like on the most recent past value that is known. Okay, it can be shown actually that if you can easily prove this, and we do these things in EE 531. If we are given, for example, xk minus 4, this xk minus 4, xk minus 7, I don't know, x0. The probability that xk takes on the value ik, given all of these values, would be equal to the probability that xk is equal to ik, given xk minus 4. So This characterizes a Markov chain. Now, a Markov chain is time homogeneous if what? The probability that xk equals j given xk minus 1 equals I is independent of what the time index k is. Okay. Now, the transition probability matrix P is defined as the following. Now, the transition probability matrix is the matrix of entries Pij, where Pij is the probability that xk is j given xk minus 1 is I. So it is the matrix of the probabilities of going from state I to state j. I to j. Now, in a time homogeneous Markov chain, the probability of going from I to j does not depend on when we do this transition. It does not depend on the time index k. Okay. So if we have a time homogeneous Markov chain, and it is entirely characterized by this constant set of values, or the matrix of values Pij. Now, a Markov chain can have a finite state space or an infinite state space. In the case of a finite state space, S, whatever the size of S is, we'll have that size. Suppose that the size of S is M. We would have M cross M entries, right, in the transition probability matrix. But in general, the state space may also be infinite. Okay. Now, all right. So we'll now think about P, the vector P of k, which is the vector P1 of k. Now, in the rest, without loss of generality, we will map the elements of the state space to positive integers. I mean, because it is at the end of the day, S is a countable set. So if it is a countable set, we can map the elements to counting numbers, right? And it will make our notation easier. But you understand that the states can be anything. If you want, we're giving numbers to the states. Now, what is P1 of k? Or in general, what is Pj of k? P sub j of k is the probability that the state at time k is j. Now, we're interested in how this probability vector evolves in time. In many of our analysis of networking situations, we have a state that evolves with time, right? So what is the dynamics of this system? Well, it is really easy to see that by the definition of the state transition probabilities, the probability of being in state j at time k can be found by summing the probabilities of being in state I and going from state I to state j, right? By the definition of the state transition probabilities and by total probability theorem. So I can write this vector as the product of the vector at time k minus 1 times the transition probability matrix P. This is the equation that gives us the dynamics of the Markov chain. Okay. Any question here? Is this clear for everybody? Oh, Narva just arrived, so let's look. Is this clear for everybody? So let's see. Now, question: when this dynamic, as this dynamic evolves, is there a stationary point such that does there exists a pi, vector pi, such that pi equals pi p? Meaning, if there's such a vector pi, it would mean that so that pi corresponds to the probability of being in each state. And the probability does not change once we're in pi. It does not change in the next time step. So basically, what does that mean to you? It's like a steady state, right? This would mean a steady state. Because, for example, if there are two states, okay, I'm in with probability 1/3, I'm in state 1, and with probability 2/3, I'm in state 2. And if I apply pi times p, I find again 1/3, 2/3. This means that in the next time step, I am again in state 1 with probability 1/3, state 2 with probability 2/3. It means that the probability vector has converged. Now, this is called a, if so, okay, pi is called a stationary distribution. Okay, once you get there, things are stationary, nothing happens. Probabilities of each state have converged. Now, now, if there exists, now there may not be a unique stationary distribution, by the way, right, for every Markov chain, but if there exists a unique stationary distribution, does the limit as k goes to infinity, p of k, converge, I mean, equal to pi for all initial states, initial probability vectors. Okay, so there are two notions here. The one is there a stationary distribution? Is it unique? And if it is unique, I mean, there's a unique pi that solves pi equals pi p. Does it really, is it really reached? I mean, does the probability dynamic, the probability vector, does it really converge to pi? Because there are situations where there is a solution to pi equals pi p. However, the Markov chain is so-called periodic, and there's no convergence. Okay, so these are questions about stationarity and ergodicity. To, you know, to sort of go one step further, if there's a unique steady state, the Markov chain is ergodic. Okay, but even if it is ergodic, that doesn't mean there's going to be convergence. For there to be a stationary distribution, first of all, the Markov chain has to be aperiodic. Okay, so let's go now one step at a time. Let's work out an example. suppose our P matrix is very simple, 1, 0, 0, 1. Now, how about the solution of pi equals pi P? How many solutions does this have?
Sonsuz sayıda hocam.
Exactly. Any vector pi will be a solution of this. Okay. So any pi will solve this. So basically, this degenerate case happens because if you plot this Markov chain, I mean, not the plot, if we graphically represent the states, state 1 and state 2, from state 1, you go, if you're in state 1, next time you are again in state 1 with probability 1. If you're in state 2, you'll be in state 2 again. So, so if you start in state 1 with a certain probability P1, so pi 1, and if you start in state 2 with another probability pi 2, then forever you are in state 1 with probability pi 1, state 2 in probability pi 2. And this does not mean that basically this does not mean that there's any convergence that happened, basically. The network, that doesn't mean that the Markov chain converged to a stationary distribution. Okay, this is an example of a case that the Markov chain is not irreducible. It can be, in fact, reduced into two separate classes. So again, to give you, okay, let's provide another definition at this point. Let Pijn be the n-step transition probability from states I to j. Okay. Now, j is reachable from I if there exists an n such that Pij of n is bigger than 0, meaning there is a certain finite number of transitions that can take you from I to j with positive probability. Meaning, it is possible to go from I to j in a finite number of steps with non-zero probability. That means I is reachable, j is reachable from I. Now, based on this, a Markov chain is called irreducible if any state is reachable from any other state. Any state is reachable from it. So in this example, if you look at this example, 1 and 2 are not reachable from each other. Now, let's see another definition. So Pij n equals probability x k plus 1 n equals j given 1 moment. Given xk is I. Now state J. Oh, this is the same definition. Sorry, let me just, for some reason, I thought this was different. Okay, so let's erase this. So based on this, let's give you an example. There are two states, A, B. And the Markov chain behaves as follows. So pictorially, numbering A and B as 1 and 2, this is what happens. If you're in 1, you go to 2. If you're 2, you go to 1. Okay. Now let's solve pi equals pi p. What is the solution? The solution is 1/2, 1/2. Then for example, if the original vector of probabilities is 1, 0, meaning we start in state 1 with probability 1, then next time we know that we are in state 2, and at time 3 we know that we are back in state 1. So what happens? The pk vector does not converge. Okay, what is this case? What's going on here?
Burada da periyodiklik problemi var galiba hocam.
Exactly. So in this case, the p vector is periodic. It will keep oscillating. For example, if we start like this, oops, if we start like this, then every odd time we will be in the same probability vector. If every even time instance, it will be reversed. So there's no convergence. So if you find yourself in this situation, you cannot talk about a stationary distribution. Let's define the notion of probability. Sorry, the periodicity. Formally, states I is said to have a period d sub I greater or equal to 1. If d sub I is the greatest common divisor of a number of transitions such that pii of n is bigger than 0, meaning so pii of n greater than 0 means you can go from state I back to state I in n transitions with non-zero probability. Now, if all of those possible number of transitions from I back to itself have a greatest common divisor that is bigger than 1, it means that the state I is periodic with that common divisor. Now, if Pij of n is 0 for all n, that's possible. There's no way to come back, meaning there's a way to come back, but it is 0 probability. We say that di is infinite. Now, if di is 1, I is aperiodic. Okay, the greatest common divisor of trips durations from state I back to itself is 1, then state I is aperiodic. Number 3 is a Markov chain is aperiodic if all states are aperiodic. All right. So let's see a lemma. Every state in an irreducible Markov chain has the same period. How would you prove this? Think about it. How would you prove such a result?
Ben şöyle düşünürdüm hocam. Mesela i'ninci state'ten tekrar i'ninci state'e n adımda dönüyorsam bir şekilde bir circle oluşuyor diğer state'lerden
Evet.
dolaşarak. Dolayısıyla circle'ın üzerindeki başka bir state'e de n adımda dönebilirim. Yani onun da periyodu n olur.
So
Ve irreducible
essentially,
olduğu için tüm circle, yani circle'da tüm state'lerde mevcut olur.
right. I mean, essentially that's the idea, right? I mean, if you can go from I to I in di steps, then to go from j to j, you can first go to I and make an arbitrary number of loops, and then go back to j. Suppose j had a different minimum greatest common divisor. J had a different greatest common divisor. You would reach contradiction, but of course, this is not a full proof. You can, as an exercise, read the proof in the textbook. So here's a theorem that all of these things culminate in. A finite state space, irreducible Markov chain, has a unique stationary distribution pi. If it is irreducible, it will have a unique solution for pi equals pi p. And if further it is aperiodic, then the probability vector p of k converges to pi for all initial states of the probability vector.